Today we're going to be talking about how to find magnitude and angle of a resultant force. And in this particular problem, we've been given two forces. We'll call them force 1 or F sub 1 and F sub 2. Our first one, which we'll call F sub 1, is a force of 200 newtons acting in this direction. We can just think of this as a vector with a magnitude of 200. And we know that the angle between this vector, or this force here, and the positive direction of the x-axis is 60 degrees. Then we have this other force, which we'll call F sub 2, acting in the negative direction of the x-axis with a magnitude of 300 newtons. If you imagine that these two forces are pulling against each other, what we want to do is find a resulting force of these two forces and the angle between that resulting force and the x-axis. So what we mean by that is, here you can imagine we have this force of 300 newtons in this direction and this force of 200 newtons in this direction. So there's slightly more force being put in the direction of this green arrow here than this orange arrow. So if we just were to take a guess right now and look at where our resultant force might be, it's going to be somewhere between these two forces. We're putting more force on this green arrow here, so our resultant force is probably somewhere about here maybe, and this is rough, but it's going to be slightly closer to this 300 Newton force than this 200 Newton force because there's more force in this direction. So our resultant force will be somewhere around here. We want to know the magnitude of that force, in other words, the length of the vector, and also the angle that's created between this resultant force and the positive direction of the x-axis. So the first thing that we need to do in order to figure out those two things, we need to model F sub 1 and F sub 2, these two forces, as vectors. Let's deal first with F sub 1, our first force here. What we need to remember is that by the definition of vector addition, or the triangle law, this force here of 200 newtons, this vector, can be modeled by two separate vectors. One that has the x-coordinate that contains the x component here and goes from the origin to this terminal point right underneath our terminal point of this 200 Newton force, and then the second vector which starts from this terminal point and goes up to the terminal point of our original vector. So we can model this original vector of 200 newtons by adding together these two vectors here. So here's what we're going to do. We're going to say that F sub 1 is equal to the magnitude of our original force here, which is going to be 200 newtons. So we say the magnitude, we multiply that by cosine of 60 degrees because we're looking again for the x value, the length of this side here. We want cosine of 60 degrees like this, and then we're going to be multiplying that by I, because remember I corresponds to our x component. That takes care of this first blue vector here, this horizontal one. Then we're going to add to that this vertical blue vector, which is going to get us, when we add these two together, our original vector here, F sub 1. So when we do that, we're again going to say the magnitude of 200. This time we're going to multiply by sine of 60 degrees. Sine of 60 degrees, that's going to give us the y component, the vertical component. And we're going to be multiplying that by j, which corresponds to our y component. Now, if we look quickly here at our unit circle, essentially what we have here is a vector in the direction of 60 degrees. Well, 60 degrees on our unit circle is in this direction right here, 60 degrees, out to pi over 3. And what we know is that the x value there, if we go here along the x value, we've got our x value and our y value here. It's given by this coordinate point right here. The x value is 1/2, the y value is √3/2. So what we can say then is that our cosine of 60 degrees value, our x value, is 1/2. So we'll get 200 times 1/2, the x value of the coordinate point from our unit circle, plus 200 times sine of 60 degrees, the y value from our coordinate point on the unit circle, which is √3/2, and we're going to multiply that by j. When we simplify, we see that we get 100i plus 200, and the 2 are going to cancel to be 100. We're going to get 100 √3 times j. Now we have this in the form of a vector. This is also equal to, we can put it in this vector form here, 100 comma 100 root 3, like this. Now if we write out here force 2, we'll say F sub 2 is going to be equal to, again we do magnitude, which in this case is 300 for this other vector, 300 times, again we want our x component, so we're going to say cosine, which gives us x, of 180 degrees, because this was 60 degrees here, but coming from the x-axis and moving all the way over here to this green vector is 180 degrees, so we'll say cosine of 180 times I plus 300 times sine of 180 times j. Now when we simplify this, again we can use our unit circle. We know that, according to our unit circle, cosine of 180, the x value of the coordinate point at 180 degrees, is -1. So we'll get 300 times -1i plus 300 times the sine value at 180 degrees. That's the y value at 180 degrees, which is equal to 0, and we multiply by j. When we simplify, we just get -300 I, and this j component goes away completely. And this should make sense to us because since we only have I left over here, this tells us, and because the value here at 300 is negative, it tells us that we're moving in the negative direction right along the x-axis, that there's no vertical component where we go up along the y-axis or down along the y-axis because there's no j component involved. So we have just -300i. This translates to vector notation of -300, 0, like this. Now, when it comes to finding an expression for the resultant force, we'll call the resultant force F sub r, the resultant force. All we need to do is add these two together. So what we'll do is we'll take this notation here and this notation here and add them together. We'll get 100i plus 100 root 3 times j plus a -300i, or just -300i. When we simplify, we'll see that our resultant force is going to be equal to -200i plus 100 root 3 j, and we can also write that notation as -200, 100 root 3 in vector notation that way. So there's an expression for our resultant force. Now we need to find the magnitude and the angle of the resultant force. Remember that magnitude is really just the length of the vector. Well, when we have vector notation like this, we can use the distance formula to find the length of this vector. Remember that this vector notation basically tells us that we start at the origin, the point 0, 0, and we go out to the coordinate point -200, 100 root 3. So our distance formula, we can say distance of the resultant force, or length of the resultant force vector, is going to be equal to square root of, we take our x value here, -200, and we subtract 0 because the initial point of this resultant force vector is the origin right here. Remember where we started it. It's going to end at the terminal point here, -200, 100 root 3, like this. So we say -200 minus 0 because this point here, 0, 0, so we're using the distance formula to find the distance between these 2 points here. So -200 minus 0 squared plus 100 root 3 minus 0 squared, like this. Now when we simplify to get the length of the vector, you can see we'll get -200 minus 0 is -200, square it, and we get 40,000. Then we get 100 root 3 minus 0 is 100 root 3. When we square it, we get plus 100 and 2 extra zeros. 10,000 times 3 is going to give us equals 40,000 plus 30,000, which is going to be root 70,000, like this. If we convert this to the square root of 10,000 times 7, we can take the square root of 10,000, we'll get 100, and we'll see that the length of our resultant force vector is 100 square root 7. If we do that on our calculators, we see that that's approximately equal to 264.6, so we'll say 264 0.6. Again, this is the magnitude or the length of the vector, and because the magnitudes we were given are in newtons, we're going to say that this is 264.6 newtons is the magnitude of our resultant force. Now we just need to deal with the angle between the resultant force and the positive direction of the x-axis. So that's this angle right here, positive direction of the x-axis to our resultant force. What is that angle right there? We already know the magnitude, we need the angle. Well, here's what we do know. We know this angle right here. We know this angle. We'll call this angle theta right here. We know it because we know that this coordinate point is negative 200, 100, root 3. So if we just draw a triangle right here that goes out to the terminal point of this vector, and we call this a right angle 90 degrees, then this angle theta can be found with this formula where we say tangent of theta. Remember that tangent is equal to opposite over adjacent. Well, opposite side, this side here, we know that this triangle here has a height of 100 root 3 because that's our y coordinate. This is 100 root 3. We also know that the length of the adjacent side here is 200 because this coordinate point here is negative 200, the x value. So the length of that side is 200. So if we say tangent of theta is equal to opposite over adjacent, 100 root 3 over 200, we can say that tangent of theta is equal to root 3 over 2. If we solve that for theta, we get theta is equal to arctan, or the inverse tangent function, of root 3 over 2. So this is helpful because that gives us this angle here, right? This pink angle here. But what we really need is this angle here in purple. Well, all that we have to do now is say that this full angle here from the x-axis, the positive direction of the x-axis, all the way over here is pi. Remember, according to our unit circle, half of a circle here is pi, or 180 degrees. So we can express this purple angle as pi, the entire half circle, minus this small piece here. So we'll call this angle that we want of the resultant force, we'll call it theta sub r, just like we had d sub r. So we'll say theta sub r is going to be equal to pi minus arctan, or the inverse tangent function, of root 3 over 2. If we calculate that using our calculator, what we see is that theta sub r, the angle between the positive direction of the x-axis and our resultant force, is approximately equal to 139.1 degrees. That's the purple angle that we were looking to find between the positive direction of the x-axis and our resultant force.